In the last video for topic 4.1 special relativity, we're going to look at why it is that no object can travel at the speed of light in a vacuum. Now when we're talking about an object, we're talking about something that has mass. So anything that's massless, like a photon for example, can actually travel at the speed of light. But anything that contains mass won't actually be able to reach that speed. And we'll have a look at why that is. You can note here that we're really just talking about the speed of light as being a universal speed limit. In order to make sense of this, we're actually going to go back to the equations that we've already dealt with, and the ones in particular are going to be time dilation, where the proper time interval is dilated to the relativistic time interval, length contraction, where the proper length is shortened to the relativistic length, and finally relativistic momentum. So by looking at these equations, we're going to tie back into a part of the equations that's common, and that's that term of the square root of 1 minus v squared over c squared. And so I'm just going to jot those equations down again on the left hand side here. So t is equal to t naught over 1 minus v squared on c squared for time dilation. L is equal to L naught multiplied by 1 minus v squared on c squared. And for relativistic momentum, PV is equal to m naught v over the square root of 1 minus v squared on c squared. Now, you'll often see these shortened or summarized, I suppose, in these forms. So T is equal to gamma multiplied by T naught. L is equal to L naught divided by gamma. And PV is equal to gamma multiplied by m naught v. So they're the shortened versions, and we need to talk about what this factor of gamma is. It's known as the Lorentz factor. And as you might have guessed, the Lorentz factor incorporates that square root term. So gamma is actually just equal to 1 over the square root of 1 minus v squared on c squared. And we're going to focus now on that factor because it ties into all three of those relationships. So to understand that in more detail, we need to look at the range of values that we're going to get for different speeds. So if we start out with v being much less than c, then you can see there, as we've done in previous examples, v squared over c squared is going to be very small. So 1 minus a small number is close enough to 1. That's going to give us the result that the Lorentz factor is going to approximately be 1. Now that's the situation that corresponds to Newtonian physics, so the physics that we experience on a day-to-day basis. If we then consider what happens as v approaches c, so that means that v is going to get closer and closer to c, we're going to see that gamma is actually going to get closer and closer to infinity. That's because as v gets closer to c, v squared on c squared is getting closer to 1, so 1 minus v squared on c squared is getting closer to 0. That means we're going to have 1 divided by a very small number, which will give us a number that gets closer and closer to infinity. That scenario is what we would usually refer to as relativistic speeds. Now, if we try and look at what happens when v is equal to c, we end up with v squared on c squared being equal to 1. So we have this situation where the Lorentz factor is equal to 1 over 0, and as we know from maths, that is an undefined quantity. So that means that we can't have a speed that's equal to the speed of light because the equations here start to break down. Now if we try to take it even further, if v is greater than c, then that means we're going to have v squared on c squared being greater than 1, so we're going to have 1 minus something bigger than 1, and so that means that the Lorentz factor is going to be 1 divided by the square root of a negative number. So I'm just going to write that as square root of a negative there, and in mathematical terms that becomes an imaginary number. So we can't really have an imaginary number in our real universe, and so you can see there that we can only get up to a speed that approaches c, so something just a little bit less than c. Otherwise we end up in this situation where the maths breaks apart and we can't physically define the quantities of time, length, and momentum. So to summarize that, objects with mass are not able to travel at the speed of light, and the reason, as I just said, is because those quantities become infinite in the case of relativistic momentum. So that's the key factor. If you try to increase the momentum of something and it has to be infinite, that's going to be a problem. We don't have enough energy in the universe to allow something to travel with infinite momentum. Likewise, if we consider the times involved and the lengths, we can make some statements about those, but ultimately it's about relativistic momentum. But we can also identify that time intervals become infinite as well. And lengths will actually decrease to 0. So there's why objects can't travel at speeds equal to or greater than the speed of light. To try and make more sense of this, we're going to have a quick look at a Desmos graph as well. On this graph, you can see the vertical axis is plotting the Lorentz factor. The horizontal axis, we're going to have v over c, so really just the fraction of the speed of light that the object is moving. You can see a red dot that corresponds to the Lorentz factor for the speed being equal to 0. As we increase the speed, you can see that there's not much change initially. And if we stop at 0.1 times the speed of light, you can see that there isn't really a significant change at all. If I show the coordinates of that point, you can see that the Lorentz factor is only 1.005. Now, that corresponds to a proper time interval of 1 hour, giving a relativistic time interval of 1 hour and 18 seconds. So not a massive difference between the two. Lengthwise, a 100 meter long object would have been length contracted to 99.50 meters. So again, 50 centimeters shorter, but not anything that's significant and not anything you'd really notice. If we continue to increase the speed, we'll move up to a speed that corresponds to a fraction of 0.5 times the speed of light. So you can see again that there isn't a significant change as we move along. And at the speed of 0.5 times the speed of light, you can see that the Lorentz factor has increased marginally, so it's now 1.155. And again, to put that into context, 1 hour of a proper time interval would be 1 hour 9 minutes and 18 seconds for a relativistic time interval, and a proper length of 100 meters would have been length contracted to a relativistic length of 86.58 meters. So the effects are starting to become a little bit more noticeable at 50% of the speed of light. However, the effects are going to be much more significant when we have, say, the Lorentz factor being equal to 2, so that would be a doubling of time and relativistic momentum. So if we stop at that point, that speed's at about 0.866 of the speed of light, and so in that situation, 1 hour for a proper time interval would be 2 hours for a relativistic time interval. Likewise, an object that's 100 meters in length would now be length contracted to 50 meters. Now, as we continue to increase the speed further from there, you'll notice that there is now a drastic increase in the Lorentz factor, so much so that it'll go off the top of the graph. You can see that we actually have a vertical asymptote when v on c is equal to 1, so in other words, where the speed is equal to the speed of light. So that line is never actually going to reach a value of 1 for v over c. If we now come back and have a look at a couple of key points on that graph, for a Lorentz factor of 4, the speed there would be about 0.968 times the speed of light. So for the Lorentz factor to double from 2 to 4, the increase in the speed has gone from 0.866 to 0.968, so an increase of about 0.1 times the speed of light. If we now look at the doubling of the Lorentz factor from 4 to 8, we would have the speed being 0.992 times the speed of light. So an increase of 0.024 times the speed of light. So you can see there that doubling from 2 to 4 requires a much greater increase of speed than from 4 to 8. If we go even further to look at a Lorentz factor of 16, that corresponds to a speed of 0.998 times the speed of light, so an increase of only 0.006. So you can see there that the closer that the object moves to the speed of light, there's a much more significant increase in the Lorentz factor. So ultimately, when we're looking at relativistic physics, we're really dealing with speeds that are much greater than about 0.5 times the speed of light, so usually in the vicinity of 0.8 or 0.9 or even higher. And so there you have a good graphical representation of why it is that objects cannot move at the speed of light in a vacuum.